Hi everyone, my name is Evgeny Potapov. I'm CEO and co-founder of RichScope. We are doing a GPU observability platform. But before we start, I wanted to check how many of you do neural network training? Good. And how many of you are familiar with DevOps, have DevOps experience? Good. So I work in site reliability engineering and DevOps in 2008. And during this time, I was working with different kinds of businesses, banking, trading, startups, social networks. And what's common about them is basically the infrastructure stack. So if you know how to do observability for, let's say, any web application, you can come to any other business like that and organize proper reliability, proper scalability, proper observability. But there is something new. And basically that's what happened over the past couple of years, and it's large-scale neural network training. And the problem there is that basically it's uncommon comparing to any kind of web development. It's uncommon comparing to any kind of enterprise software. And problem here with a lot of DevOps people doing observability for GPU training, for neural network training, is that because from perspective of a typical DevOps person, neural network training is a very, very boring thing. What DevOps people think is that how the training is happening. You spin GPUs, you spin hardware for training. Engineers, ML engineers prepare the training itself. They start, and then a lot of people think nothing happens for next couple of days, next couple of weeks, and so on and so forth. But it's actually different. In a recent Meta paper about Llama LLM training, Meta reported that over the period of 60 days when the Llama was trained, they had over 400 of different failures, different interruptions of training, of which only half was the hardware, the GPUs. The other half was different kind of application level problems. And 400 metrics over 60 days, it means that basically problems were happening over each 3 hours. And that's actually a big problem because GPUs in a lot of cases are expensive thing, and if the training stops, you still pay for hardware that does nothing. It's not only that. There is a recent ByteDance paper where they talk about how ByteDance organize reliability for their infrastructure. And they say that they have over 6,000 jobs failing over the period of 3 months. And if we calculate this by, let's say, for instance, even 16 GPU cluster, it's over $100,000 wasted if you just spend time on trying to recover from such issues. And what makes it so different from a typical web application observability? In typical web application observability, in typical software application observability, where everything happens on CPU, you are used to metrics. If CPU is used by 100%, it means CPU is used by 100%. If RAM is used by 100%, it means your memory is completely used. If disk is used by 100%, that means your HDD through output is completely used. But what's different with GPUs? Basically, instead of having one single central processor, CPU unit, GPUs has a lot of so-called streaming multiprocessors. So there is a central CPU unit that gets the program that is going to be executed on CPU. And then the data and the program is shared across multiple small processors units that do very basic mathematical operations. But as training process requires processing a lot of data, that's precisely what GPUs are doing. And what's different comparing with typical CPU processor usage is that once this program is loaded onto GPU, the GPU utilization is kind of like 100%. But that doesn't mean that the application, let's call it application, it's called kernel, is doing anything useful. Because if there is a problem with data load, if there is a problem with network configuration between different GPU servers, GPUs might still be used by the application, but they might not be doing something useful. So basically, there are two important metrics. If you would ask me, what simply two most important metrics that you need to collect if you will only have option to watch the cluster, I would say that you need to watch two variables. One is GPU engine active, which means that GPUs are utilized with loaded programs. And another is SM active metric that basically says that GPUs are doing important work. They're calculating. Further, I want to talk about 5 most common failure cases that happens during the GPU training. But again, as I said before, basically from a high-level perspective, all of them might be reduced to the idea that you need to watch for the case when the GPU is used but does nothing, like streaming multiprocessors are doing nothing because of some issues. So what these issues are? Okay, so we are doing training. Training takes days or weeks, and anything might happen. There might be network problem, there might be overheating of GPUs, there might be problem with the disk storage. So if we do not save intermediary data, then if the process goes down, we lost all the data. So we need to do checkpoints. Basically, we need to save files with the current state of training. But the problem is that even for 32B model, the size of the checkpoint is almost 400 gigabytes of data. Now imagine you work with some like Microsoft Word, where you click Command S, Control S, and that means saving 400 gigabytes of data. It's a challenging process itself. But at the same time, you need to save the data, because if you will lose the data, you will pay for nothing of this GPU cluster. There is one thing that I want to tell again, considering all the cases. There is no single metric that you can watch. It's always a correlation of metrics that you need to look for and then compare. Checkpoint itself happenings in two kind of ways, synchronous or asynchronous. And when the checkpoint happens, the training stops and the file is saved across different processes, across different nodes, and then the training recovers. It happens depending on the amount of checkpoints per steps that engineers decided to do. But as a person who's responsible for observability of the system, you need to watch how frequently it happens. Let's say you decided, or engineers decided, to do checkpoints every 5 minutes, and doing checkpoints every 5 minutes will mean that the most of the time you'll be saving this 400 gigabytes of data and not doing the training. So you need to decide what amount of checkpoints you need to do. And for regular checkpoint observability, for checking the checkpoint, you need to compare your SM activity once GPUs are doing the training along with the throughput of the disk storage. So you see that SM stopped, disk usage or network usage increased, and that means a checkpoint. But that's fine. So we need checkpoints. But what, as an observability engineer, we need to do is to watch that this period of time doesn't increase. And because saving 400 gigabytes or even more and more and more of data typically happens over the network storage problems are frequent. And what might happen is that on day 1 everything's good. Checkpoint takes 5 minutes. Day 2, day 3 is the same. Day 4, there is a performance degradation in network, and checkpoint started to take 20 minutes instead of 5. And in case of synchronous checkpoints, when the training stops and then the checkpoint is done, this whole amount of time will be increased, and that will mean increased training time. There are 3 kind of metrics that we need to watch together to get the insight of the checkpoint time. First thing is that we need to see either for host file performance throughput. Other thing is that we need to watch for PCIe bus throughput, and we need to compare the kernel length amount with memory processing. So basically, if we see that there is a SM engine stopped, launches fall to 0, and at the same time there is something writes to the disk, it means the checkpoint happening. So again, what I want to say, you can't get simply dashboard with a single chart, or you can't collect different dashboards and think they are separate. They are never separate now. With LLM training, with neural network training, there is no single chart anymore. It's always number of metrics correlated, or it's always a couple of charts that you need to look together. The other and the most painful thing is a distributed hang. So the thing is that, let's consider we run a huge training. We have 128 GPUs. The thing is that all the training is happening in parallel. So the problem is that the whole training lives as long as every process doing the training lives. So basically we have, let's say we have 8 servers with 8 GPUs. We have 8 processes running, and if any process goes down, you have all other 7 processes waiting for one single process to come alive again. And there are 3 kind of these hangs that might happen. One is called rendezvous hang. That happens, so basically we have distributed processing system. All different processes need to sync at some moment in time the data they process. So basically during the training, each process takes a part of the data to process, and then they need to synchronize the whole results together. In many cases, even in large clusters with dozens of servers, there is a single process called coordinator that accepts the information that the sync now needs to be done. And if this process goes down, or this process have network issues because of different kinds of problems that might happen, network again, some server problems, whatever, all the processes will stop and they will try to reconnect, and they will do nothing until this coordinator process will work again. So ideally, you need to keep an eye that this coordinator process is working, and ideally, you need to keep an eye that processes are not idle. Again, as I said, if you have only 2 metrics, you can watch again for utilization versus SM activity, and if SM activity does nothing, there is a problem. You need to investigate something. The other case is idle problem, and that's what not so obvious for people not from neural network training process. Again, you have a lot of different servers. Single process goes idle because, let's say, disk subsystem is used a lot. This single process becomes idle and does nothing, and all other processes at some moment in time, they stop and wait until the synchronization event, and they again do nothing. And if the problem is happening for hours, or if you don't see that process went down, the whole training will be stopped. The third case is frozen collective. Collective is a synchronization procedure that happens between different processes. So while idle case is a kind of like a part of frozen collective, frozen synchronization process, there are additional cases when this might happen. So let's say one of the processes, they call ranks in neural network terminology. One of the processes starts to process a bigger amount of data than others. And or there is a mistake on how specifically the synchronization will happen. There is a once way of this defined in one of the processes because of some if statement, and the other do the other case of coordination. Again, the system stops and nothing is happening. And again, utilization shows 100%. So there are like easy case, and there is a much more sophisticated case on what might happen. Easy case is basically some host level problem. Because of something, the CPU is used 100% on the server. Because of something, simply the process can't do anything or it's killed. Then it's good, you can watch the server problem with the typical observability software. But there are a lot of cases when something happening inside the application. And once it's happening, you need to know the data that will help you to understand where specifically the problem happened. There is one important thing during the PyTorch training where you can enable the dump on timeouts of the ranks processes. And you can define a size of this dump. And you can watch the process and see if any of ranks, any of processes of applications working on nodes stopped. If you stopped getting the data or you got the data on timeout, that means you need to jump in and understand what's happening. You typically stop the whole training, you have the checkpoint, and you need to recover the process, find out what the problem is. If it's an application level problem, then you can enable debug level state. You can enable these environment variables and then start the training again, kind of like on a debug level, not on production because it's very slow, and see what specifically in what place of code led to this application level problem of synchronization. There are different ways of synchronization data across the servers. And in code, there might be an issue. Let's say there is such and such condition when one of the processes will try synchronization of one kind, and the all other processes will try to synchronization of another kind. And that won't match. Then for simple cases, you can do host stack sampling as well. And if you see that host stack sampling means that when you see the process stopped, you can try to understand what caused the process to be stopped. It might be a file system problem, and that means the process was stopped because it was trying to access something, let's say access the data. It might be a problem with locker futex, and that means that there is a data loader problem that tries to load the data and have issues. And it might be nickel, so-called nickel weight, where it means the frozen collective case. Again, you can consider kernel latch versus engine activity, and if you see that there is nothing happening, but in terms of lengths, but engine is used 100%, then it's a problem with synchronization. And if nothing happening, there is a problem happening on host. So again, you get different metrics, you try to correlate them, and because of that, you can easily jump. Not easily, it's always hard, but you can faster jump to try to resolve the problem. The other problem, again, which is from my perspective even worse than the previous, is so-called straggler. Again, it's not only that processes are alive until every process is alive. The timing of each step takes the longer time of the, like the slowest time of the process. So if you have a lot of different processes, a lot different ranks doing a good job, but if you have one of processes slow, there won't be another step until this specific process will finish. There are different reasons on why it might happen. It might be always you have different servers, and different servers communicate via network protocols. Let's say network protocols. It might be, and it's most likely InfiniBand between different servers, but as we have problems with home internet, there are sometimes problems with network connectivity between servers. And if one of processes experience this network problem, then you have the whole process being slowed down. One important thing why is this a bad problem is that you won't see easily that there is a problem with training even with SM active monitoring. If you don't keep an eye on what's happening, your training might take 2 weeks instead of 1 week, 2 days instead of 1 day, and you'll pay for this time. And this is happening because just a single process takes longer time than every other. Simple thing to watch is that you can look for CUDA events and understand per process step time how long each process step takes. You can collect this data together and you can see that, let's say on a chart, that one of processes timing increased, and that means you need to keep an eye, and that means you need to jump there as soon as possible. The other problem, why it's so sophisticated, is that I said before that SM utilization, SM activity is a very important metric. And I said that if it's used, then it's good. But there are some cases when it's actually a problem. So let's say we have a problem with one of processes, with one of ranks, when it processes much more data than any other process. This will mean that SM activity will actually increase comparing to regular processes. So if you see that one of one of processes uses much more computing power than other, it might not mean that it does a good job. It might mean that there is a problem with data processing there. Then what I said about network link degradation, you have metrics about the network problems. What I didn't said is that basically every metric I'm talking here comes from NVIDIA's DCGM, data center GPU monitoring, I believe. And there is a Prometheus exporter that extracts the data and allows you to build this in Grafana or whatever. I'll ask guys to share the presentation, so you won't need to make pictures of the slides right now and just trying to copy paste it later. And one more metric is about the PCI Express replay, because some problems might happen between different cards on a single server. Then there are two kind of cases that are more about the hardware. Again, if it's more than a single server, they need somehow to be connected together. It's usually InfiniBand protocol, which is very, very fast. But there are frequent cases, especially at GPU hostings, when InfiniBand has problems and the processing degrades to typical TCP IP, what we're using in regular networks. The thing is that InfiniBand is at least 2 times faster than TCP, and frequently even much more faster. So if any kind of network problem is happening, because of every process need to be communicating with each other in terms of synchronization, the whole training process will be delayed if this is one thing that's happening. You can watch for different kind of network metrics to understand what's happening there, and you need to keep an eye on network as the cluster grows, if you have many servers, this is a bigger and a bigger risk to happen. On a single server, you won't have such problems. On 2 servers, less likely. But if you have a large cluster, it might happen frequently. And the other thing is that I wanted to talk about is the slow GPUs themselves. There is one important thing that we need to know. So usually we think of GPU throttling or CPU throttling as the processor was overheated and throttling started, like frequency of processors is degraded. But for past 5 or 6 years, I believe, there is another kind of throttling happening. And that means when the power consumption of the device of CPU or GPU increased, and that will mean the degradation in terms of frequency of the processors, because data centers care about the power usage. So there is a limit on power usage that might be used by the training process. Power, I mean like electricity power. And while if you like watch for a basic metric like temperature of the processor, it might be still good. But there it might be happening power throttling that will degrade the process of training. And the main fundamental thing is that, again, as I said, there is no single metric to watch for each case. It's always a correlation of different metrics, and you need to consider this a lot while you do training. You can do eBPF prods for processing profiling. You can do DCGM checks for hardware counters. You especially need to watch for what your training process is put into stat out, because there is a lot of information related to that. And you need to correlate all of them to see what's happening. The problem is that it's not easy to do this. I mean, you have Grafana, you have any kind of observability platform, and you need somehow to correlate this data. And what you can do is you can do some dashboards, you can try to put charts together, but it's really hard and it's like a case-by-case basis. What I would suggest you, well, basically we are doing that, but what I would suggest for kind of like an open source solution, if you're able to, if you are not having a lot of data, is that you can, instead of having the dashboards in Grafana, you can collect all this data to Prometheus. For instance, you can collect all this data to Victoria logs, ClickHouse, whatever, and you can put Claude code inside the cluster, inside the observability cluster. If you'll be able to log in there, if Anthropic won't block you, you'll have CLI tool for analysis of what's happening. And still Anthropic doesn't block Claude -P process, where you can do on cron prompts saying, please check the observability metrics to see if everything goes good. You can do a skill that will ask for specifically this correlation from metrics, and you can do this on a cron basis job. You can at least get the information from Claude, and you can ask for structural data that you can send to your alerting system and get this information in time. The main thing is that you need to keep an eye on what's happening, and you need to do it frequently, because GPUs are expensive. If you don't have hardware installed in your office, company, wherever, you rent it, GPU costs $3 per hour. If it's 16 GPUs, it's already something like 3 by 16 by 24, around $1,000, right? Okay, let's say around $1,000. So it's not a job of doing it like one time in a couple of days. And it's not very easy to put alert notifications in such metrics. You can put alert notification on temperature. You can put alert notification on throttling. You can put alert notification of overall GPU utilization going down. But it's not easy. You can't do the alerting that your SM processing goes down because there are checkpoints. So SM goes down from time to time. You'll get hundreds of notifications about, like, false notifications about problems. So what I say again is you need to find the way to correlate. And the easiest way right now, if you don't have too much observability metrics, is to put Claude or Codex, something like that, to the server and do cron jobs where you find the problem. I hope this was useful. I'm not sure if you guys all do the observability, but at least I hope that you will be able to understand what kind of problems might happen and how to look for them. And if you have DevOps people taking care about the cluster, you can share the presentation and ask them to do more observability. Thanks.
Thank you very much. It's surprising that now you also need to monitor the voltage consumption of data center too.
And the problem is that if there is a small degradation of the GPU and you do very proper training where you load your CPU's SMs for 100%, if there is a very small degradation of power usage devices, the throttling is going to happen.
Yeah, so now in question times, let's not just ask question, wait until our will bring microphone to you. So let's start, the first question and then answer.
Okay, thank you so much for your talk. It was really interesting. Yeah, I want to ask one question. So you've told about profiling the whole cluster, but I want to ask, maybe you had some experience with profiling GPU kernels, their latency, their compute intensity. Yeah.
There is so-called thing called eBPF. eBPF is a kernel level profiling doing the very low overhead. And you don't need to do instrumentation for this. Recently, in past year or so, I think, there were some developments in eBPF profiling of libcuda and other libraries. There is one open source library doing this, I believe. You can just put like GPU monitoring eBPF on Google and find it. Other thing is our product. But generally, for any kind of like a low-level profiling of kernel types of collective running, amount of collective running, a lot of additional metrics from libcuda. You can use eBPF for GPUs, Google, or come to me and we can do like a free pilot and get the information.
You have a question here.
Maybe you know something like single GPU instance TUI, a tool which allow us something like GPU top good enough for the metrics which you described on your presentation.
There is NVIDIA SMI, but it's like two metrics.
Right?
NVTop does good job, and there is also DCGM. For consumer cards, there are not too many metrics. I believe for consumer card, even SM usage, you can't get it. But at least you can try to DCGM and DCGM Prometheus exporter.
Thank you for the talk. You've mentioned that you have to track and correlate multiple different metrics, and that's what your product does. So what is your main approach? Is it rule-based, based on the experience of the team? Is it machine learning-based? What do you use to correlate?
Answer this question without
yes.
advertisement of your company.
I can try to reframe it in terms of installing Claude Code on a server. There are two things that you can do to get the better investigations using Claude Code, for instance, if you have all this data. Claude Code does a very good job right now if you will ask Claude to create skills based on, you can literally say it, based on best practices of machine learning observability on GPUs on the web. So Claude Code after that will create skills, and that skills will be very useful. Other thing for correlation, you can get this presentation, feed to Claude Code and ask to create skills as well. That's what I will do actually. No, not about presentation. I mean that's what I will do generally. And you can also try to do several investigations and then ask Claude to check the session, its own session, and ask what it would improve, and to ask Claude to put this in skills and then use it in later. The only problem is that to get all these like skills, you need to have the issue first, so you need to catch it yourself. But Claude generally, even without skills, will do the job pretty well. The only question is the amount of data that needs to be processed. If you have 2 servers, if you have 4 servers, Claude Code is enough. If you have much more, you need to find a way how to process the data.
Yeah. Any other question?
But we basically do AI agent. I mean, why I'm talking about Claude is because AI agentic way to correlate metrics is the best way.
I think I now understand how your product works. No? Maybe we have time for... We have time, so we can ask, but we don't have questions. Okay.
Okay, so one question.
You have one. Okay.
Yeah.
Please.
So,
Please wait.
Let's say I want to train some big model. I need some big GPU cluster. Maybe I will just use GCP or Azure ML or something. So your methods observability is for if I wanted some custom version. Let's say I rented some piece of data center, and but nobody helps me to make this work. Like, but in GCP they probably do this, right? I'm not sure. It's just a general question.
They will allow you to do hard. You will still need to do your own observability. I will suggest it because, first of all, GPU pricing on GCP is insane. You will pay like $6 per hour for a single GPU card. So you will want to make sure that the performance is well. The problem with GCP is that it's only like a very, very top level of application profiling and hardware metrics. But there are a lot of problems when the one rank might get slow, not because of GPU problems, but because, let's say, this one specific process got a bunch of data that it's harder to process than other cases, or the process got a lot of memory and was killed because of using a lot of memory on the operating system. So ideally, you need to get, let's say, the simplest thing how you can, you want to do the cluster. You need to install Prometheus everywhere. You need to install typical Prometheus exporter everywhere. You need to install DCGM and DCGM exporter everywhere. You need to collect all the data to, let's say, Victoria metrics and Victoria logs. And then you need to get some, again, Claude Code or Codex that will be doing frequently checking the data and correlating it.
yeah, thanks. Just one clarification, maybe I misframed the question. Not GCP, but particularly Vertex. Maybe. So do they do all of this under?
A lot of things, of these 5 problems, 3 are purely application in a lot of cases. And you decide how you will do checkpoints. You need to find the balance. Every 5 minutes, most of the time, the process will be saving files, not training. You need to somehow see that this is happening, and it's again application level. So you need to go deeper. Prometheus is pretty fine. Prometheus metrics are pretty fine. But